to be the last obstacle between you and the dinner, so thank you for coming. Today I would like to describe you what we do at Verbit to ingest massive amount of data coming from sensors and field devices, and to deal with them when we secure this kind of data into a column database that we use to implement our source of truth dealing with IoT, Internet of Things data records. So this is a typical architecture that we use. So basically what we do is to ingest data coming from a variety of appliances and devices deployed in the field. And we typically do that using Lambdas on Amazon Web Services, or using HTTP endpoint to collect the data. And all these streams are secured inside Apache Cassandra, which is a quite well-known column database that we use. And after that, the problem is to use this kind of data records, because Cassandra is quite rigid in terms of query models. So you are only allowed to extract the data with specific patterns, depending on the partition keys that you use. And so the problem is to satisfy the customer in terms of the patterns that you want to use in order to extract the data, because in many cases the customer wants to extract the data applying custom filters or custom workflows in order to extract the data, operate on them, and create an indicators or aggregated pieces of information that is interested in. So we have to fight against Cassandra in order to satisfy those kind of requirements that the customer has. And to do that, we typically use a streamer-based approach, because as we will see in the presentation, in general, reactive streams have a very powerful semantics and a very powerful expressiveness that allow you to work very easily with this rigidity of Cassandra. So we use, in particular, Akka streams in order to extract the data and to prepare the data to create sort of data marts or materialized views of the data that we secured in Cassandra in some more elastic data repository. And we usually use Amazon Redshift for this kind of things. So we materialize the reports that the customer, we materialize the reports that the customer wants to consume in this kind of storage using Akka streams and fetching the data out of Cassandra. And once you get this materialized view, for instance, in Amazon Redshift, then you can use common tools like BERT or whatever you use in order to generate reports and graphical user interfaces and dashboards and all the things that the customer expects from you. And of course, using this operation based on Akka streams, you can also feed real-time processing engine like Kinesis in Amazon, or also Ignite, Apache Ignite, or in general any engine that you can use in order to apply rules on the data that is flowing in real time, and that you can extract either directly from the Lambda or from Cassandra. So in general, you have a series of pain points that you have to solve dealing with data ingestion in telemetry and machine-to-machine, and in general in Internet of Things application. The first aspect is to ensure data quality. In general, you gather different kinds of data records from the appliances and the field devices, and it is not always the case that the data quality that is generated from these things is high enough. So you must be sure to have a tool or a set of tools that allow you to operate on the data and to improve their quality and to give them a context that you can use when you extract them and you elaborate them. Then, of course, you have to guarantee fast data access, so guarantee low latencies when it comes to generate reports and indicators that the customer wants to extract out of the operational data that you collect. And another important aspect is that the things that you store in Cassandra in terms of data model, in many cases is completely different with respect to the domain model that the applications expect. So you have to have a way to completely detach the structure of your events and data records that you save in Apache Cassandra or in general inside your source of truth with respect the structure of the data records that you emit at application level. So the domain level and the data structure in general are quite different. So again, you have to design, you have to think about a way to decouple these two aspects, one with respect to the other one. And then, of course, you have to guarantee a seamless and elastic scaling of your architecture because as you register new devices, then you have to guarantee that the system keeps being responsive and fast in order to guarantee the second point, the fast data access. Another aspect that we find very annoying is the notion of immutability of events. Because in general, we are taught that as soon as we secure our events and our data records in our column database, they are forever, so they are immutable. And we soon discover that this is not always the case. And this is not always the case for several reasons. I listed some of them. For instance, we may have no longer relevant fields, and we simply want to drop them out from the original data records. Misnamed keys, that's another reason why you have to amend your events that you just stored in your column database, in your source of truth. There could be missing pieces of information, or also accidental privacy or security leaks. For instance, passwords accidentally stored inside your data inside Cassandra. And of course, you can also have requirement changes that force you to rewrite somehow the history of your data records that you store inside your column database. So in general, what we do is to rely on a single source of truth to store our data records coming from the device. And as I said, we use Apache Cassandra for that because that technology provides us with the requirements that we have. So no single point of failure and very low latencies in terms of data access and a very powerful scalability. But this is just the beginning, because then we have also to address all the pain points that we just saw in the previous slide. So the first problem that we have to solve, as I said, is to overcome the rigidity of the query model provided by Cassandra. So in general, if you want to extract the data out of this kind of column database, you have to think about extracting the data, specifying all the keys that you designed as your partition key. So in particular, Cassandra used the notion of partition key to distribute the data across the cluster. Okay, so you compose a partition key, for instance, speaking about n-series, a reasonable candidate for a partition keys could be a combination of the device ID, the temporal bucket, we'll see in a while why we use the temporal bucket, and the measure ID, so the source of the measure streams. And then once you specify all these keys, then you can extract the data record that you are searching for. So if you do not specify a key here, you get an error. So it is important to retrieve the data being consistent with the partition key that you created. And on the other side, you have to use a partition key, because otherwise you cannot distribute evenly your data across the cluster. And this is a very no-no practice using Cassandra. You must distribute your data evenly across the cluster. And that means that you have to choose this key, this partition key, wisely. So typically, this is why you introduce also a temporal bucket in your partition key. So for instance, you define a monthly time bucketing, or a daily time bucketing, or a minute of hour or hour of day time bucket, and you use this specific key as a partition key in order to distribute the data of a specific sensor or a specific measure ID across your Cassandra cluster. So, for instance, speaking about time series, then to satisfy the Cassandra requirements of spreading your data evenly across the cluster and minimize the number of partitions read, and you have to design a sort of partition key in this way. So for instance, device ID, temporal bucket, let's say a monthly temporal bucket, and the measure ID. So as long as you extract the time series, the timeline for one single measure ID, this approach is quite trivial, okay? You just have to specify the device ID, the measure ID, and then the series of temporal bucket that you want to extract. Let's say if we are speaking about a monthly time bucket, you start from January, February, March, and so on and so forth. But the point is, what I have to do if I want to extract the status of the device? For instance, I could be interested in knowing the last reported measure for every measure ID pertaining to a single device. Now it's starting to be quite annoying because the query that you have to use are a little bit more involved, okay? Then you have to, in theory, extract several temporal buckets and several measure ID because, of course, each single measure could be associated to a different temporal bucket because it is not guaranteed that you get all the measures of the same device ID at the same time. So it could be the case that I get one measure in November, the other one in January, and so on and so forth. So you have to combine different queries together in order to extract the last known status of this thing. And this is quite annoying. But here is where we introduce the power of reactive streams expressivity. Because in general, reactive streams offer you quite a wide set of built-in stages and operators that somehow simplify these kind of operations on top of Cassandra, for instance, extracting the data using multiple queries. And in fact, if you think about it, getting the last known status for a device, it's like composing a graph. You start from a source, which is the series of your temporal buckets, and out of the buckets, you fan out a set of queries, each query pertaining to a different measure ID, and using the buckets that are generated from your source. And then you can merge the different results that you collect from the different queries together, taking the first result for each device ID, and then you can merge all the records together, providing the sequence that represents the device status. And now we'll see that Akka streams is a very powerful way to translate this kind of graphs in running code. So I think it's very powerful because no matter how complicated it is, your query pattern that you want to use to extract the data, you can always model this query as a graph, and then you simply translate the graph in a set of built-in stages of Akka stream, and then you execute the stream, and you get your and you get your result. And in fact, maybe we can. Okay, I don't know if it's readable, but so let's say that we want to spread the data around our Cassandra cluster using a monthly time bucket. Okay, so here what we are doing is to generate an iterator of our temporal buckets. So each month has a corresponding entry in our iterator, and we use this iterator to define a source. So here in the last line, we are telling Akka to generate an integer source, our temporal buckets representing the month, with this builder here, source.fromIterator, and we specify our buckets iterator. So with this very simple snippet, we create our source in the graph that we saw before. And after that, the next step is to define the queries. So here we are defining the branches of our graph, okay? So what we are saying is that for each time bucket, this integer here, we want to emit an event. So the event is actually what we retrieve out of Cassandra, okay? The data record stored in Cassandra. So basically we have a for loop here, and we generate a number of flows, And each flows is a sort of transformation of the temporal bucket and the device ID into a DTO, into an entity extracted out of Cassandra. So here we simply specify the query to extract the data records out of Cassandra. Okay? So now we have this, the source of temporal buckets, the fan out that provides a query to extract the data records out of Cassandra. What is missing here is the merging operation. Okay? So we can define the sink as simply a sequence of events, and then we can wire all these things together. So here we simply take all the pieces that we defined in the previous slide, and we connect them together using the Akka streams operator in order to create a graph. So here we have basically the interesting part, which is the place where we take all the branches of our graph, we connect them together, and we create exactly this structure. So the DSL provided by Akka streams is a very convenient way to materialize this kind of drawings, this kind of graphs, into a Java code. I have to say that in Scala is cleaner because the syntax is less verbose, and so you can appreciate this aspect even better. But also in Java, if you follow the logic of this snippet of code, it's quite simple because you have a builder, and you from this Akka stream builder you wire all the pieces together. So the source, the sink, and the branches of our graph in order to create the closed loop shape, the closed shape that you want to run. And once you have the closed shape, then you invoke the akkamaterializer, and you turn basically the graph into the result that you are searching for. So before using Akka, this piece of code was an entire library of Java-based code developed in-house. It wasn't a very huge library, but yet was several hundreds of lines of code to be maintained and to be operated. Now with Akka streams, it's just a matter of 50 lines of code, even less. So it's very powerful, and it also offers the possibility of adding interesting filters or aggregated operation on top of the data that you extract. So I think that the benefit is very interesting. As I said, Akka streams is very expressive in the sense that offers you offers you a rich set of built-in stages that you can use in order to operate on the data. For instance, another delicate aspect dealing with the column database and Apache Cassandra is pagination. So Akka streams and in general Reactive streams has this fold operator that allows you to get through different pages of your data and process each page as it is collected out from the database. Then you can combine different streams together. You can apply transformation or concatenation of different streams together. You can, in particular, this take operator was used in my status example to limit the number of records to 1, because for each measure ID, we want just one measure because we are searching for the last reported measure for that measure ID. So you can limit the number of emitted records out of the stream and so on and so forth. So you have a very rich set of operators that are built-in stages. I just reported a few of them, but if you go to the Akka streams manual pages, you can see how many and how advanced they are. And the nice thing is that the Akka stream machinery also works in OSGi. So you can expose the actor materializer, for instance, as a service. You can register it in the service registry, and then you can use wherever you want in your bundles. So again, this is not very readable, but maybe we can. Okay. So basically, the Akka guys provided this activator, and this activator basically allows you to configure the actor materializer that you need in order to run your streams. So it's just a matter of overriding this configure method here, providing the required configurations, and to register the actor materializer as an OSGi service in your service registry. And once you do that, of course, it's very simple to use it, because all you have to do, for instance, in the bundle when you are dealing with time series, is just to reference the actor materializer and inject the reference of this service and just use it. So if you remember, this materializer was used in order to materialize the graph of my previous example. Okay? So then another nice thing about Akka streams is that they are reactive. That means that if you take this graph that we considered before, you can imagine all the bullet as subsequent stages of a sort of job which is performed by the Akka machinery. And the nice thing is that these stages talk to each other in an asynchronous and non-blocking way. So in case the source is emitting too many records and something in between cannot cope with this number of records, then somehow it can tell the source to slow down. And this is performed asynchronously. So basically what you get is a safer environment where there are more chances of avoiding out-of-memory errors or resource problems, let's say. So, and all this thing is built in. So you don't have to do practically anything to implement it. And in particular, if you think about data ingestion, where you could have thousands and thousands of devices pushing new data records into your system, then you can combine this back pressure, this reactivity of Akka streams with HTTP components. For instance, Akka has a very interesting component which is a sort of HTTP server that you can use to expose a POST method, a REST API. And this REST API can be combined with the back pressure, and it simply blocks as soon as all the subsequent stages can cope with the data rate that is generated by the device posting new data against the REST API. So again, this is almost for free and allows you to keep your system safe and free from out-of-memory errors. Okay, so probably the Akka documentation can say what is back pressure better than me, but more or less is what I tried to describe before. So it's just a control mechanism that slow down event emitters as soon as subsequent stages perceive that they cannot cope with the rate of emitted data. So it's a very convenient way to slow down the system and avoid resource problems. As I said, it is almost for free, so all the stages that you use to implement your graph, to implement your stream, are already back pressure enabled. So everything in the chain will communicate to each other in order to enforce this back pressure mechanism. And so now the last point is to address the last pain point that I was mentioning at the beginning. So the coupling between the data model and the domain model. As I said, they can diverge very soon in the development of a new application or in general inside your environment, because the customer adds newer and newer requirements on how the data records should be shaped or structured. And this is, of course, you cannot mirror that requirements directly inside your storage, because modifying or altering the data model is one thing, but altering the schema of your database or the columns of your key space or of your column families is completely different aspect, is more job and is more difficult. So what you can do is to, leveraging OSGi dynamicity, what you can do is to inject what we call event adapters. Well, we do not call them. It's after the Akka terminology. But in OSGi, you can register new bundles that offers this kind of event adapters as OSGi services. And in the process of extracting the data out of Cassandra using Akka streams, you simply inject this event adapter in order to alter or modify the data structure of the DTO and map the DTOs into the classes, into the structures that the application layer is expecting. And this is particularly interesting because you can have multiple event adapters registered for a specific time series, and you can pile up different event adapters as your requirements changes, or you are provided new requirements by your customers. I want to add field, I want to transform that field. You simply register a new event adapter, and then you can maintain your events in Cassandra immutable. And as I said, it's very interesting that you can also have different versions of this kind of adapters inside your systems. And you can combine the semantic versioning enforced by OSGi with the message versioning. So what we do is to define the version of the message, the version of the serializer that is doing the marshalling and unmarshalling operation on the data records that we store in Cassandra. And then we combine these versions with the message adapters in order to generate the right data structures that are expected by the applications and the upper layers. So in general, dealing with time series in Internet of Things application, we saw that it's a matter of choosing a very scalable, high-performance solution and to adopt it as your unique source of truth, because it's very important to have a single source where you stash all the data coming from the different devices and appliances that you are managing. But this source of truth is not enough, because the query model, the query patterns, the supported query patterns of this source of truth are not enough to satisfy the customer requirements. So you have to have a way to extract in an agile way the data out of the source of truth and to materialize specific views and specific data marts for your customer. And we use Akka streams for that. And in order to decouple the data model and the domain model, we leverage the dynamicity offered by OSGi and the event adapters. So, to quickly demonstrate all that, we can run 3 minutes. Okay. Maybe we can run this test. Okay, so this is basically a carafe environment, and here we registered the feature for Akka streams. And so if we now query for the service of actor materializer, why changed it? Okay, we see that we have our actor materializer offered as OSGi services in the system. So now you can reference it in order to implement the piece of code that we saw in the presentation. And actually, this test is performing a test against the status method. So if we go here, here we are generating the data, and then we are calling this status method, which is nothing but the method that we saw before in the presentation. So if we run this, we simply collect the last reported measure associated with the measure ID pertaining to the device that we are querying. So it's I'm sorry, but it's not very readable. So it's very easy to operate the Akka streams machinery inside OSGi, and in few lines of code you can overcome the limitations of Cassandra query patterns and in general of column database limitations like Dynamo or technologies similar to those. So that's it.